Okay, I think that we can get started. Thank you all for being here. Thank you for joining in. My name is Matteo Lencioni. I'm a product manager at Move Solutions. Today, the topic of today's webinar is dynamic monitoring. But before that, let me just introduce the company. Well, Move Solutions is a company that designs and manufactures structural health monitoring systems. The company was born, I would say 5 years ago at this point. The founder and current CEO of the company was working at the time with an engineering firm, and he basically patented a system for dynamic displacement detection. Shortly after that, unfortunately, we had here in Italy, because we're based in Italy, we had the Morandi Bridge collapse. A lot of people died. So at that point, there was a lot of attention around, structural health monitoring with a specific focus on dynamic monitoring. And that's how we were able to grow within that year. And then we were able to expand first to, the rest of Europe, and then to Australia, and a couple years ago to the United States as well. Well, before talking about, okay, there it is. Well, before talking about today's topic, I think it's interesting to introduce the system operation first. So as you can see on the left of the page, this is how basically how our Move Solution system works. So on the left of the page, as you can see, there is the sensors. So the sensors detect the data. We're talking about wireless sensors. They can detect the data, and they send the information to a gateway. The communication protocol is the LoRaWAN. So it is a long-range, low-power communication protocol that gave us the possibility to have, for all of our sensors, somewhere in between 2 years and 8 years of battery life, depending on the type of sensor, depending on how you use the sensor, and depending on the settings. At that point, once the information is on the gateway, there is an internet connection, an LTE connection, that gives you the possibility to send data to the servers. The server is where the data is stored. It is where the data is processed with specific algorithms depending on the use that we're doing with that data. And then there is the output. Well, the default option would be the Move Solutions Cloud Platform, where you can see the data. But there's other options as well. There's the possibility to implement MQTT and FTP connectors to send data to external databases, or we can expose the APIs to have a full integration into a different platform. So going back to the dynamic systems and to dynamic monitoring, let me talk about the dynamic sensors for a second, which is going to be necessary to understand the algorithms. So we're basically talking about three main sensors. The first one is probably one of the most important ones, is the accelerometer. The accelerometer is, well, quite of a common sensor on the market. The thing is that Move Solutions accelerometer can have, and depending on the settings and depending on how you use the sensor, you can have completely different monitoring. So you basically have two main working modes. You can have the sensor working on trigger, so you can set an activation threshold, and whenever that threshold is surpassed, you get a reading. So you basically filter out all of those vibrations that you're not interested in. And that's one working mode, and it's specific for one type of dynamic monitoring that we're going to see later in the presentation. The other possibility is the programmed synchronized acquisition. So regardless of the threshold surpassing, you can have you can set a certain cadence, and you can have synchronized programmed acquisition. Synchronization is up to 50 microseconds, and the synchronization is between different sensors on the same structure. So different sensors on the same structure would have synchronized acquisitions, and And that is extremely helpful for modal analysis, again, that we're going to see later in the presentation. So this is the first sensor that we have, extremely versatile. The second one is the DEX sensor. The DEX sensor is the sensor that we patented at the beginning of our story. It is a dynamic displacement sensor. So it is basically has an inertial system inside that gives you the possibility to, it works on threshold. So again, you can set an activation threshold. When that threshold is surpassed, the acquisition starts. And the acquisition is basically the dynamic displacement during the vibration. So you can really have in millimeters, you can really see what is in that point where the sensor is installed, what is the dynamic displacement of that vibration. And it is extremely interesting, again, for dynamic monitoring in a couple of different ways. We'll see that. And then there is the vibrometer, which is kind of a standard sensor in its application. I mean, basically, it's just a vibration monitoring system that gives you the possibility to monitor the level of vibration that a structure is undergoing in certain scenarios, for example, around construction sites. So whenever you have a source of vibration, which is close to, for example, to a building, well, you install the vibrometer and you can either decide to set your own threshold, or you can decide to select a certain regulation and be compliant with the regulation. So the regulation would automatically set all of the alert thresholds so that you can, again, be compliant with that specific regulation that maybe is the regulation of your country. The last one is the gateway. So the gateway, of course, is an extremely important device because it gives the other sensor the possibility to talk to the servers. So the gateway would talk with the LoRa communication protocol, would talk to the sensors, and it would basically get the information, get the data from the sensor, and then with an LTE connection would send the data to the servers. So let's dive into the dynamic monitoring. First, I would like to explain a little bit of what the difference is between the static and dynamic monitoring, because the world of monitoring, of structural health monitoring, again, can be divided into these two categories. So the static monitoring would be, as many of you might know, would be the monitoring of slow movements that the structure is undergoing. So let's take an example. The easiest example that I can think of is a tilt meter. So you put a tilt meter on a structure. The tilt meter is a static sensor. The information that you get from that sensor is how the structure is moving on the long term. So the goal at that point is the detection of any change in terms of rotations that happen to that structure. Okay, so the detection of the changes. The dynamic monitoring is a different types of system. Basically, what you do is the analysis of the vibrational behavior of the structure. So you look at the motion of the structure during the vibrations. And at that point, the goal is prevention. Because we'll see that, but what you can do with the dynamic analysis and the parameters that you can get with a dynamic analysis basically give you the possibility to detect the same change that you would later detect with a static sensor, but early on. The typical example would be, let's say in the medical field, the typical example that we always give would be the difference between, I don't know, maybe if you have a patient that has a tumor, difference between, detecting the tumor by looking at the person or touching it from the outside, or maybe, and that would be the static monitoring, or doing a full MRI, and that's what would give people would give the doctor the possibility to detect the illness, the tumor, early on in its development. So this is what the dynamic monitoring can do to a structure, that an early detection of that same change that could be detected later with the static monitoring, but earlier. Okay, so when it comes to dynamic monitoring, we can divide it into three different categories. This is the way we see it. we can divide it into 3 different categories depending on what you're looking at with that dynamic monitoring. So if you are interested in, let's say, analyzing the vibrations in terms of their amplitude, so you want to understand how wide and so how energetic those vibrations are, and maybe you want to be notified when a vibration is bigger than a certain threshold, where in that case you're doing a peak analysis. But you can also, and this is probably the most interesting category, the modal analysis. So you can go deeper in understanding how the structure vibrates with the specific purpose of detecting certain parameters that are extremely interesting to understand the structure's health. Well, at that point, that's a modal analysis. Or there's a vibration monitoring. It's basically the one that I was talking about when I was presenting the vibrometer. It's basically just the standard vibration level monitoring that you have in structure when you think that, nearby the structure, there might be a source of vibration that might, put the structure in danger. Well, at that point, you just want to have a continuous level of vibration monitoring. Well, that's what we call vibration monitoring. We will just talk about that extensively later in the presentation. So let's start with the peak analysis. So the peak analysis, again, is the monitoring of the amplitude of the vibrations. So you look at the vibration in their amplitude. That's the interesting information that you're looking at. And it can be a short-term or a long-term peak analysis. Let's look at the short-term peak analysis. That's basically what I was talking about a couple of slides back. So it is just, you basically have a bunch of sensors on your structure, which are, I'm talking about accelerometers and DEX sensors in this situation. So you're basically, the raw data, let's say, would be the acceleration or the dynamic displacement. And you have a bunch of sensors all set in trigger mode. So the sensor have an activation threshold. Whenever that threshold is surpassed, you get the reading. As you can see on the right of the slide, you have a reading from an accelerometer on 3 axes, X, Y, and Z. Okay, so if you have a threshold surpassing, you get the reading. The purpose of this type of monitoring in the short term would be the detection, a real-time alert of exceptional and unexpected behaviors. So, for example, oversized loads, strong winds, earthquakes, those environmental conditions that would cause, strong vibrations in the structure. You might be interested in, monitoring it by setting an alert threshold and being notified if the vibration is wider than that specific threshold. The reason might be, there might be a lot of reasons. For example, if we're talking about a bridge and maybe that bridge has a traffic limitation. So certain types of vehicle should not be allowed to across the bridge. Well, having a dynamic system that basically gives you a peak analysis in the short term. So setting an alert threshold on top of the activation threshold. So setting an alert threshold, if that threshold is surpassed, you get the notification, basically gives you the possibility to be notified with, oversized loads. Another one would be the long-term peak analysis. So, let's say you have a certain number of sensors and all of them are in trigger mode. Let's say, the sensor are activated 300 times a day, 250 times a day. So you basically get 250 readings per day, which are, again, with the example of a bridge, are the consequence of 250 vehicles passing over the bridge. On the long term, let's say in 30 days, you have thousands and thousands of vibrations. Of course, every single one of them has a different peak-to-peak value. That's how we call it. So it's basically the maximum amplitude of that vibration. So every single one of them has its own peak-to-peak value. But the interesting thing is that the traffic on average on the long term is kind of constant. So you can do a statistical analysis on that data, and you have thousands and thousands of acquisitions, and you can see it on the right of the page. So what you see here is basically the distribution of those peak-to-peak values. So you can basically, and this is what we can do with our algorithms, we can just have a statistical approach, and we can tell you what is the average value of that peak-to-peak vibration, and at the same time, we can give you statistical parameters to understand that distribution of values better. For people who are interested in, deep statistical parameters, we can give you a standard deviation. So at that point, you can just look at that distribution, exactly at that moment of time for that period of monitoring, what is the average value of that amplitude of vibration. And if we're using a DEX sensor, you're using a DEX sensor, so that's in millimeters. So you know exactly on average with that traffic, on average, what is the amplitude of the vibration of your bridge in that point. And you can see if it's changing on the long term. So if a year after that, that mean value changes with the same traffic, statistically, if it changes, it means that that something has changed within the structure, which might be, it's stiffness, for example, because with the same load, the structure is vibrating with a different amplitude. So maybe the stiffness has changed. And that might be a sign of, in the long term, that might be a sign of structural degradation. So this was the peak analysis, so the analysis of the peaks, so of the amplitude of the vibration. At the same time, we can have the modal analysis. So the modal analysis is gives you a deeper understanding of your structure. The purpose would be basically there is a lot of literature behind it. So what we know is that there is certain parameters that you can extrapolate from a structure that basically represent what we call the ID of the structure or the fingerprint of the structure. So there are certain parameters which are, as you can see here, the frequencies, the model shapes, and the damping. Those factors, those parameters only depend on the geometry of that structure. So if you have a change in those parameters, that automatically means that you have a change in the geometry of the structure. And it's an early sign of structural degradation, because as soon as something changes, and I'll give you some examples later, as soon as something changes in the structure, you automatically see those parameters are extremely sensitive. And so you automatically see some trends of variation in, for example, the frequencies, which are calculated with an algorithm which is called the FDD, frequency domain decomposition. So what we do, we install our dynamic sensors on the structure. They're synchronized. So we perform a modal analysis. We detect those three parameters that are so important for the structure. So we create that ID of the structure, that fingerprint, and then we keep monitoring those parameters on a daily basis every single day for the next month, year, 2 years, 5 years. And we can see how those parameters change. And so we can see if there is something changing in the geometry of the structure. And this is basically, this can have two different purposes. Again, prevention of structural damage. So you're monitoring for changes in those parameters. Specifically, those changes might be variation trends in the frequencies, or, for example, asymmetries in the shapes when you do model shaping. But at the same time, might also have a different purpose. So let's say you have a structure that is not new, it's kind of old, or maybe even if it's old, but you have a FEM model, because a FEM model of the structure, so a computer model of that structure, can provide the exact same values that you can detect with a dynamic monitoring. So what you can do at that point, you can do an experimental setup with our sensors. You can do an experimental evaluation. You can determine those parameters with our system, and then at the same time, you can compare them with the theoretical values that a FEM model, a computer model of the structure, would provide. So basically, you have the experimental values and the theoretical values. Comparing them gives you the possibility to see to do an assessment of your structure, to understand whether it is in good condition with respect of its theoretical values, or if those values are matching, or if those values are different. Sorry. Yeah, I mean, so this was the modal analysis, and now let's go to basically let's get to the last category, which is the vibration monitoring. As I was saying, the vibration monitoring is definitely not something new. It's new with the wireless sensor. Basically, what we do with vibration monitoring, we install vibrometers on the structure with the specific goal of basically keeping an eye on the vibration level that the structure is undergoing, because we might be worried by maybe a construction site that is nearby. So whenever there's a construction site, actually in many countries, by law, you have to monitor for vibration in the neighboring buildings, because the neighboring buildings might be undergoing some stress because of the vibration caused by construction. So at that point, sometimes you have to measure and you have to monitor for the vibration. The vibrometer goes exactly in that direction. So there's two different possibilities. You can have a custom mode if you just have your own threshold in mind, and you can just set your own alert threshold and say, okay, I do not want this vibration threshold to be surpassed. And you get, again, notifications whenever it is surpassed. At the same time, you can have a vibration monitoring being compliant with a certain regulation. So you can, like, the sensor gives you the possibility to set a regulation, which might be the RI 507 for the United States or others. And at that point, all of the thresholds are automatically set accordingly to that regulation. So are the threshold that regulation specifies. So you don't have to set your own threshold. It's the regulation that sets the threshold, and you just get notified whenever those thresholds are surpassed. Both in terms of, again, at that point, the vibrometer would detect the velocity. So the measure that stands for the vibration level is the velocity in millimeters per second. And you just get notification whenever those thresholds are surpassed. Again, the goal is avoiding, and preventing structural, but also cosmetic damage to the structure. And this brings us to, well, a couple of case studies. These are not actually case studies, but just possible applications. So let's look, for example, at buildings and vertical structure. So whenever you're monitoring a building and a vertical structure dynamically, what is worth doing? So, well, again, a peak analysis for unexpected peaks of vibration. So you have dynamic sensors on the structure, all of them set in threshold mode, so that whenever that threshold is surpassed, you get a notification. Maybe, I don't know, during a storm, you have high winds that cause huge vibrations in the structure. So you might have all of those sensors in trigger mode, and whenever you have those strong vibrations, get notified. Or maybe in areas where there's a lot of earthquakes, again, same reason. So you have that side of the dynamic monitoring in place. And then at the same time, you can have a modal analysis. So you look for modal parameters, frequencies, shapes, damping on the long term with a statistical approach, which would be the OMA, operational modal analysis. It's basically just what I was talking about before. It's just looking at a huge amount of data, of vibrational data, statistically. And then there is this FDD algorithm that just takes in all of those vibrations and basically gives you the frequency response of your structure with the detection of all the frequencies of vibration of the structure. Those parameters, again, change only if the geometry of the structure changes. So you get peak analysis. You can have peak analysis, modal parameters, and then you have maybe vibrational levels if you have a source of vibration nearby. Maybe you have an underground, a subway just, I don't know, passing under the building. And so that causes vibration that you may want to monitor. And at that point, you can just monitor constantly the vibrational levels with the vibrometer and being compliant with certain regulation that you can set. well, pretty much same thing about the bridge monitoring. In bridge monitoring specifically, I would say that, frequencies, shapes, so the modal parameters is probably the most important part of it, because it's really a fingerprint of the structure, and whatever changes, you can really detect it early on with a dynamic monitoring. I'm thinking, for example, of if there is a concrete bridge, I'm thinking of I don't know, the concrete aging, or so which might make the structure more stiff, and so the frequencies might just get a little higher, and so you have a trend of frequencies just rising a little bit. Or it might also be something a little bit more, let's say, exotic, which might be for example, for a bridge that is crossing a river, it might be the scour problem. So if you have had maybe some flooding in the past few weeks, and at that point you might experience some flooding around a pile, and some scour, around the pile, which is basically the exposition of the foundation of the pile. So on a practical level, what happens is that pile gets longer because the exposed part of the pile gets longer, and so that changes the frequencies of vibration of the pile itself and of the entire structure that the pile is holding up. So by monitoring dynamically your structure, you can really understand that. And well, the vibrational levels in a bridge is typically interesting really only if there is a construction site maybe close to the pile, or if there is some work that is done to the pile itself and you want to make sure that that is not causing an acceptable level of vibration. So you can use a vibrometer to monitor that. The last application that I think it would be worth mentioning when it comes to peak analysis with our DEX sensor, so with the dynamic displacement sensor, would be in the railway application for the ballast void. The ballast void detection is something that is really interesting because it can really prevent derailment and major problems. And the way we do it, we just put basically a DEX sensor, which gives you the vibration on the vertical axis. We put it on the railway ties, and that's how you can really understand if also the vibration in terms of the peak of the vibration, so the amplitude of that vibration, but also the frequencies of that vibration once you process the data with the FDD algorithm with the modal analysis. So that's how you can see if there is a void forming underneath the sleeper or a tie, and and that's what can give you the possibility to understand if there's some ballast void going on. Well, I am done. So I'm open to questions. Let me see. Will a recording of this presentation will be sent to all who registered? I guess so. Yep. Do you guys have any question? Let me see. Can we set triggers to switch between dynamic and static measurement? Well, the thing is that the sensor, I'm thinking of the accelerometer right now. So the sensor is extremely versatile. So you can actually have the trigger mode and the trigger mode and the program sampling. So the one is used for peak analysis, or the one is used for the frequency analysis working at the same time. So the same sensor in terms of the dynamic measurements, it can do both things. Now, from dynamic to static measurements, let's say that it's two different sensors. So there is a sensor that can perform dynamic analysis and different sensors that perform static analysis. Mention what type of sensors are kept in deck for displacement measurement. Yeah, as I said, it's basically an inertial system that it's a system that we patented. So it is an inertial system that is afterwards compensated in order to provide a displacement measure. What is the resolution of the accelerometer? I do not have the data sheet with me, so I actually don't remember. I'm not gonna lie, but I can get back to you with that information. But anyways, you can find the data sheet on our website under the sensor section. How are acquisition for OMA managed? Not being able to be triggered, it would not be OMA with acceleration peaks. Are they timed? Yeah, exactly. So we only, when it comes to modal analysis, we only work with time triggering. So it is not a threshold trigger, it is time trigger. So we have synchronized acquisition, for example, once every hour. So once every hour, we have a stream of data synchronized for all of the sensors installed on that structure. And we run the algorithm on that entire amount of data. The OMA algorithm, basically, like the hypothesis behind it is just that the traffic, and let's say that the load that is causing the vibration is a white noise, basically, because you have all kinds of loads, you have all kinds of vibrations, so that doesn't influence the analysis. So that's the hypothesis we start from, and then we only work on synchronized acquisitions. Okay, well, it seems like we are done here. Again, for technical information about the sensors, you can just look at the sensors on the website, and there is a specific section for every single one of our sensors where you can see the data sheet. You can download the instruction manual. You can look at the sensors, and for further clarification information, whatever, just write an email, and we will be right back to you. Okay, thank you. And let me see if there's any other question. Oh, do the sensors expose API even without the gateway? Well, a gateway is necessary always, because the data travels from the sensor to the gateway, and then from the gateway to the cloud, and then to the cloud. I'm talking about the Move Solution servers, and then it's from there that you can retrieve the data with the APIs. So definitely a gateway is necessary. We have some clients that do not use our gateways. They have their own gateways. As long as it is compatible with their system, it's fine. Okay. Thank you. Thank you for joining in, and I'll see you at the next webinar. Bye.